Hi, welcome to the second video in the series on principles of radiographic exposure. In the last video, we looked at the discovery of X-rays, had an introduction to electromagnetics, and talked about atoms. I encourage you, if you didn't watch the first video, to check it out. In this video, we will continue talking about electromagnetics, we will talk about radiation, and we will talk about X-ray production. We'll start with electromagnetics. So first we'll have a review of electromagnetics. What we already know, as we know, the electromagnetic spectrum is the range of frequencies that make up one of the four fundamental forces of the universe. The magnetic field and the electric field travel in a sine wave that are transverse. That means that they're perpendicular, 90 degrees offset from each other as they travel. In this spectrum, the higher the frequency, the more energy the wave has. And that's denoted by the equation E equals F times H, where H is the Planck's constant. And the lower the frequency, the longer the wavelength becomes. The equation C lambda times F, where lambda is the wavelength, F is the frequency, can be solved for wavelength, and as the frequency, as this becomes a smaller number, this number will become a larger number, okay, and C, of course, is the speed of light. The electromagnetic spectrum, we talked about that. As can be seen, the X-rays and gamma rays are the highest energy waves. As the frequency goes up, the energy goes up. As the wavelength shortens, as we can see here, it's getting shorter, smaller number, the energy goes up as well. The visible spectrum, which is all the light that we see, is from about 400 to about 750 nanometers. The electromagnetic spectrum consists of radio waves, microwaves, infrared, ultraviolet, visible light, X-rays, and gamma rays. All of these are the same electromagnetic waves. They are just different frequencies on the spectrum. We utilize unique parts in different ways, so we give the ranges different names. The uses of the spectrum, some of these functions that range, you may already know functions that ranges on the spectrum are employed for. Below is a brief outline of the functions. So radio waves are used for things like radio and television. Microwaves are used for satellite communications. They can be used for cooking food, telephone, radar. Infrared is used for electric heaters, cooking food, and infrared cameras. It can also be used for remote controls, use infrared. Visible light, fiber optic communications uses visible light. Photography, photosensors, photoresistors for electronics, sensors and photoresistors. Ultraviolet could be used for energy efficient lamps. Sun tanning and decontamination. X-rays, which can be used for medical imaging and treatments. Crystallography and spectroscopy. Two different, crystallography and the spectroscopy are two different sciences where X-rays are utilized. Gamma rays can be used in medical imaging and treatments. Gamma rays can also be used to decontaminate food, a process called irradiation. For our purposes, we are most interested in X-rays. Now we will look further into the electromagnetic spectrum by focusing on radio and communication frequencies. As you can see in the picture below, there are many different uses of radio signals, including things like TV broadcasts, cell phones, medical telemetry. All this is in the permeability zone, so it can permeate objects such as dense buildings made out of concrete. Things in the semi-permeability zone are like weather radar, and then the 2.4 gigahertz band, which is used for hundreds of consumer devices, including Wi-Fi and Bluetooth, and then also line of sight. So things like police radar need line of sight. That means that if you're not able to see it, it won't be able to communicate effectively. It won't be able to work properly in the line of sight. All these things just communicate information. Okay, is the way that this can be thought of. All these electromagnetic waves can just communicate information. And this includes visible light, of course, and then if we just move farther down the frequencies, X-ray, up in frequency, X-ray. So X-rays is just communicating information, and when we expose the picture, we are communicating information about the subject that we are exposing, which is usually a patient, and we are just gathering that information with a detector. Okay, and down here is a nice diagram of lower frequencies, longer wavelength, and very dramatically higher frequencies, and you can see it's a much quicker wavelength. So we'll go ahead and we'll move on and we'll talk about radiation. So there's two types of electromagnetism, and they're called ionizing versus non-ionizing. Electromagnetic waves can have so much energy that they are able to harm biological tissue. We call this ionizing radiation. Ionization is the characteristic of a wave or particle to remove an electron from the orbit of an atom. So it can actually remove an electron because it has so much energy from an atom. There are other effects too that we won't be explored in this class. That will be, if you have a radio bio class or things like that, you can talk about, that will be discussed there. This creates free electrons that can have sufficient energy to remove more electrons from other atoms. The energy of the radiation must be greater than the binding energy, which we learned about in the last video, of the electron that it's interacting with. All the frequencies of the electromagnetic spectrum are non-ionizing. So there's only ionizing and non-ionizing are the two for any classification, and this is the breakdown of what is ionizing, what's non-ionizing. So the lower frequencies, of course, have less energy, so they're non-ionizing. They don't have enough energy to take an electron out of an atom, out of one of the shells of the atoms. And you see ultraviolet is in here. X-rays and gamma rays are ionizing. Okay. So there are different sources of radiation. The two main categories are medical, which is like man-made, and then background, which is natural radiation, radiation that naturally occurs. So the medical radiation comes from things like computer tomography, CT, nuclear medicine, interventional radiography, conventional radiography, fluoroscopy. The background radiation comes from things like radon, thoron, from space, cosmic rays, where they are supernova explosions, okay, and the radiation can come to Earth in the form of cosmic rays. There's internal, terrestrial, and consumer. Some internal sources are things like K40, which is in your body from potassium. K is potassium, and then C14, which is carbon. We're carbon based. Some percentage of carbon always has some carbon-14 in it, so we have carbon-14 in us. So that's like natural background radiation. This chart here is an interesting chart that breaks down the background and the medical radiation and what kind of percentage actually occurs. As you can see, there's things like occupational, industrial, but then computer tomography takes up a large chunk of medical exposure to the general populations. Background, it mostly comes from radon and thoron. Actually, radon can build up in houses that aren't well ventilated. and that can cause a big issue if you live on a mountain or you take a flight, space, which like cosmic rays can come down, can affect you more, or you receive more of them because there's less atmosphere to protect you from space. If you're on a mountain, you take a flight. Okay, so we'll move on. Now we'll take a quick breakdown of each of these types of radiation. So there are three types of radiation. They're alpha, beta, and electromagnetic waves. The alpha and beta are the particles, okay, known as particulate radiation. Electromagnetic waves are a disturbance in the electromagnetic field, which are, of course, the X-rays and gamma rays that we've learned about. We'll talk about alpha particles. What they are here, alpha particles consist of 2 protons and 2 neutrons and no electrons. So it's just a nucleus of 2 protons, 2 neutrons. So it's like the nucleus of a helium atom that doesn't contain any electrons. We call that an alpha particle. They carry a positive charge. They are barely able to penetrate skin, and they can be stopped by a sheet of paper. They are most dangerous to humans if they are inhaled or ingested. When they are either inhaled or ingested, the alpha particle can then release the radiation directly into our tissues. They are produced through radioactive decay of heavy elements, and this is a picture of what it is. So a radioactive nucleus will release an alpha particle. Okay, it has 2 protons and 2 neutrons. Another one that's our particulate form of radiation is a beta particle. It consists of an ejected, highly energetic electron or positron. They carry a negative electron or a positive, which would be called a positron. Okay, so it can be a negative or a positive. They can be stopped by a thin sheet of metal or plastic. They can cause skin damage and are harmful if they enter the body. As with the alpha, they are produced through radioactive decay of heavy elements. Okay, and this is a picture of the beta particle. Okay, so it's released from a heavy nucleus. Okay, and beta particle is released, and this is how the decay works. So decay of like a heavy element, which is like, could be like uranium-238. The atom undergoes, after a long period in some cases and shorter periods in other cases, it undergoes a decay, so it gives up energy. If it goes out through an alpha, where it's given up 2 protons, so of course what we know from the first videos, it's going to change what element it is. Okay, so it's given up 2 protons and 2 neutrons, and if you look, the atomic mass number has gone down by 4, which makes sense. Okay, now it goes to a beta decay, it goes to beta, and it goes through different processes. So each kind of like heavy element in the isotope of what it might be will go through possibly different cycles, different steps here of alpha beta decay, and then it will reach some kind of stable state. The stable state of this particular uranium atom 238 becomes lead. Okay, so and that becomes very useful to us because we use lead for protection in X-ray. The third type is gamma radiation. That the alpha, beta, and the gamma, they all come from the nucleus of the atom. Okay, so this is a third type of radiation. The gamma, as you can tell here by this picture, it's a wave. Okay, where the alpha, beta are are particles. So gamma radiation is electromagnetic waves. It has no charge. It can penetrate metals, but can be stopped by a thick piece of lead or concrete. It can produce harm for the entire human body. It is released from the nucleus of a radioactive atom during alpha and beta decay. Okay, so as you see, this atom down here has gone through some kind of decay. A particle is released. It could be alpha, it could be a neutrino, it could be any kind of particle. But it's gone. It depends what the original atom is, and then through that gamma. So energy is released in the form of a gamma ray. These are the different penetration of different forms of radiation. So there's the alpha, the beta, and the gamma that we talked about here. So alpha gets stopped by a sheet of paper, beta can go through a sheet of paper but can get stopped by a thin sheet of aluminum, and then gamma can penetrate both paper and aluminum, and a thick piece of lead will stop it depending on how thick the lead is and how energetic the gamma rays are. They can penetrate lead. Okay, and you can see the difference as, to emphasize this, that particles are modeled or are shown as a line. So this is a particle, and these are waves, the gamma waves. So now we'll sum up what we've been talking about in this graph here. There's two classifications that we were exploring, was ionizing and non-ionizing. So ionizing types are alpha, gamma, beta, X-rays, and UV, and then non-ionizing would be everything else: radio waves, microwaves, IR, UV, and light. And then there's where they originated from. So things like the alpha, beta originate from the nucleus of the atom and gamma, and then X-rays originate from the electron cloud. And down here is another reminder that alpha is a particle and beta is also a particle, and electromagnetic waves are gamma, X-rays, and UV rays. So now we'll move on to X-ray production. As we know, there's different X-ray sources. There's the man-made, and then there's also natural events. So things like cosmic rays can be, X-rays can come from stars, supernovas, quasars, pulsars, magnetars, black holes. So all these things come from space. So X-rays can be produced naturally through space. And then also X-rays can also be man-made. They can be made with a thing called an X-ray laser. They can be made with an X-ray tube, which is utilized in just diagnostic radiology. Also CT scanners, where they also use an X-ray tube, but they're used and they're set in different ways. A thing called a cyclotron produces X-rays. Nuclear power plants produce X-rays, and then even transformers produce X-rays. Okay. First, so now we'll go ahead and we'll explore the X-ray tube. Okay, we get a basic understanding of the X-ray tube and what's going on inside, so we can talk about X-ray production. Okay. As you see, our main focus is on man-made produced medical X-rays. This is done with an X-ray tube. The tube is a loop of wires, which is referred to as the cathode. On one side, in a rotating disc, so this disc right here will rotate, and that's referred to as the anode. On the other side, surrounded by an evacuated glass cylinder. So evacuated just means it has no air in it, so it's like a vacuum inside. When the tube is energized, the cathode, which this is the negatively charged side, the cathode, and the anode is positively charged when the tube is energized. Electrons build on the cathode and boil off through a process called thermionic emission. There's also another way to say it, but they boil off. The free electrons are attracted to the positive anode, so the opposites attract comes from like negatives and positives are attracted to each other. So this side is very negative, this side is very positive. When the electrons, which are negatively charged, boil off, they're attracted to the anode. On the anode, there's a target spot, which is angled. So if you can tell, there's like a kind of an angle here. It's hard to say exactly where it is, where the target spot is, but that electrons hit at a very high speed, close to the speed of light. When the electrons release their energy in the atoms of the anode, X-rays are produced. So X-ray production. The production of X-rays is very ineffective. Of the energy that is put into the tube, only about 1% to about 0.2% becomes X-rays, and the other 99.8% becomes heat. There are two types of X-ray production. They are Bremsstrahlung and characteristic. So now we'll go ahead and we'll talk about characteristic X-ray production. When the electron from the cathode interacts with the orbital electron of an atom on the anode, the electron of the target atom on the anode can be removed from its shell. In order for the anode electron to be removed, the cathode electron has to have more energy than the binding energy of the anode electron it's interacting with. The anode electron is called the incident electron, and the displaced electron is called the ejected electron through this process. The place in the atom of the now ejected electron is referred to as a hole. So the electron from the atom of the target or on the anode has now been taken off, so there's a space. This thing is referred to as a hole. If the inner shell electron is removed, an outer shell will fill in the hole, and if it's one of the outer shell that removes, this free-floating electrons will fill the hole. Characteristic X-ray is produced when the electron hole is filled in. So a characteristic X-ray is only produced when the electron fills in the hole that was created. So this is a picture of the characteristic X-ray production happening. As we can see, the incident electron comes into an atom of the target on the anode, and it has enough energy to remove, in this case, an inner shell electron, and it gets ejected. So this is called the ejected electron now. A outer shell electron will fill in this gap here, and when that happens, the X-ray photon is produced. So an X-ray is produced from this difference here, from this process here. So now we'll talk about characteristic X-rays and energy. When characteristic X-rays are created, energy from the incident electron is put into the electron it interacted with. The incident electron and ejected electron carry off energy that can interact with other atoms. So the incident electron comes in to the target of the anode, it interacts with an electron, it puts energy into it, this electron gets ejected, okay, and it carries off energy. The energy of the produced X-ray is a difference in the binding energies of the evolved electrons. So the electron here that's ejected, whatever that binding energy is, and then the energy of the electron that fills in the hole. okay, will determine what the energy of the produced X-ray is. Since binding energies depend on the element that the atom is, the energies of the resulting X-rays are characteristic of the target element. In general medical radiology, the element of the target spot on the anode is tungsten, and we can see tungsten, which is W, is the symbol, right behind us. So we talked about how tungsten is what we use for the target on the anode, and now we'll discuss the binding energies of tungsten, since characteristics is depending on what the different energy levels of the electrons are. The resulting energy of a characteristic X-rays is the difference in the binding energies of electrons involved. The equation is the energy of the characteristic X-ray produced is the energy of the inner shell minus the energy of the outer shell, the electron that comes in to fill. The binding energies of tungsten shells are seen here. The K shell, which is the innermost shell, of course, has the highest binding energy, is 69.5 kiloelectron volts. The L shell is 11.1 electron volts, and then so on and so forth, all the way down to the P shell, and all these are in kilo electron volts. So an example here, if a L shell electron of the tungsten atom is ejected by an incident electron, and a N shell electron fills in the hole. So we're talking here that if an L shell electron is ejected, okay, by the incident electron, and an N shell electron fills in the hole, what is the energy of the resulting characteristic X-ray? Okay, so characteristic X-ray is produced here. What's the energy? Well, we know it's the difference here of the inner shell, okay, minus the outer shell will be the characteristic X-ray. So the answer here will be that the energy of the characteristic X-ray produced will be the difference in the inner shell, okay, which we know is 12.1 kiloelectron volts minus 0.6 kiloelectron volts. And of course that answer is 11.5 kiloelectron volts. So from this example here, the answer is that the energy of the characteristic X-ray produced is 11.5 kiloelectron volts. The characteristic X-ray emission spectrum. So when we take an exposure, what's being produced has a certain spectrum. It has a certain range of energies. Okay, just like the electromagnetic spectrum has a certain range of energies, which are typically shown in wavelength and frequency, but as we know, that relates to energy. The X-rays produced will have an emission spectrum as well. Okay, the X-ray emission spectrum is a representation of the output of X-rays during the exposure. The characteristic energies shown are for a tungsten target, which is utilized in diagnostic X-rays. Something like molybdenum or something like that could be used, or other elements like that could be used in MAMO. So that characteristic X-ray emission spectrum would be different for depending on what the target element is made out of. So these are the energies that are made. The tungsten characteristic X-ray graph. So depending on which shell the electron is ejected from and which one fills in, a range of discrete energies can be produced. So characteristic X-ray production is known as the discrete emission spectrum. Okay, it only occurs at certain energies. It is called discrete because it only just occurs at certain energy levels. Okay, and here's a graph. This is just a one-to-one graph of the different energy levels, and these are all the different characteristic energy levels that can be produced with a tungsten atom. Okay, so All these upper ones are where a K shell is ejected, okay, and one of the more outer shells fills it in. This is where it would be K shell and the L shell fills it in, okay, K shell and more of the outer shells fill it in, and then these are the L shells, okay, and then M, N, O, okay, and then P. They're all kind of grouped together a bit, if you can tell. That these are all the K shell energies, the L shell energies, okay. So now we'll talk about the other type of X-ray production that can happen. That's called Bremsstrahlung, is the way that this is pronounced. Bremsstrahlung X-ray production. When the electron from the cathode interacts with the nucleus of an atom on the anode, the cathode electron will change its path. Okay, this is due to the negative electron and the positive nucleus being attracted to each other. So the electron, as it's coming in to interact with an atom, it's traveling very fast and wants to continue in the straight path, but it's negatively charged. The nucleus is positively charged, so that positive charge is going to attract it, the negative nucleus, to it. Okay, the amount of divergence depends on the energy of the incoming electron and how close it is to the nucleus. So the closer it comes to the nucleus, and depending on the energy level of the incoming electron, it will change how much it diverges, how much it curves around the nucleus. Energy is lost from the incoming electron, and a Bremsstrahlung X-ray is produced that is equal to the energy loss. So in this case, the electron will slow down. Essentially, it will lose energy through this angling. Instead of continuing on a straight path, now it's going to curve around. It's going to go at some kind of angle that it wasn't originally doing. And through that, a Bremsstrahlung X-ray is produced, and that's equal to the loss of the energy of the incoming electron. The greater the change in path of the incoming electron, the greater the produced X-ray. So the greater the change of path, the more energy that the electron lost, and the greater energy of the produced X-ray. The electron will continue with the remaining energy until it interacts with other atoms and loses all its energy or fills a hole in the outer shell of another atom. So this electron can continue, and it can interact Bremsstrahlungly with other atoms, or it can interact characteristically with another atom, okay, until it loses all its energy, and then it will just fill in a hole that's missing of some electron. The word Bremsstrahlung means breaking in German, so as been described, that makes a lot of sense. Okay, breaking means stopping. Okay, so the electron is stopping, it's losing energy as it's interacting with the nucleus of an atom. And this is a diagram of Bremsstrahlung radiation. It shows two different X-ray photons being produced. This one, the incident, where the incoming electron comes very close to the nucleus of the atom, interacts with it very strongly, and it diverges. It goes, close to 180 degrees back, 140 degrees back maybe, or something like that. So it produces a high energy Bremsstrahlung X-ray, okay? Whereas if the same original energy electron comes in, it doesn't come as close, it doesn't interact as strongly with the nucleus, and it doesn't diverge quite as much, a lower energy Bremsstrahlung X-ray will be produced. Bremsstrahlung, since the energy of the produced X-ray depends on the angle of inflection of the incoming electron, and the angle can be any amount, Bremsstrahlung radiation can be any energy level up to the maximum energy put into the exposure. Approximately 80% of the X-rays in exposure consist of Bremsstrahlung X-rays. So now we'll talk about the Brim-Strahling emission spectrum. The Brim-Strahling emission spectrum is known as the continuous emission spectrum. This may be obvious as the deflection of the incoming electron can be any angle, and the produced X-ray energy is dependent on the angle of deflection. So it can be any angle, so any angle between, and it's going to produce the X-rays of all different energy levels up until the maximum energy of the exposure. So Brim-Strahling, as we can see, is a continuous line where characteristic resists individual energy levels, and it's up until the maximum level of the maximum energy that was put into the exposure, which in this case is most likely 100, it seems to be. In the next video, we'll explore more about the emission spectrum, and we'll also talk about beam propagation.